Welcome back to Learn Lab. If you're new to this channel, subscribe for more tech videos. Today, we're diving into one of the most mind-bending topics in technology, quantum computers. What are they, and how do they work? Let's find out. First, let's understand what makes quantum computers so different. Our everyday computers, known as classical computers, are based on classical mechanics, the physics of Sir Isaac Newton. They process information using bits, which can be either a 0 or a 1. Simple, right? But quantum computers operate on a completely different set of rules, the bizarre and fascinating principles of quantum mechanics. Quantum mechanics is the physics that governs the universe at the tiniest scales, the world of atoms and subatomic particles. It's a realm where things don't behave as we expect them to. One of its core principles is superposition. Imagine a spinning coin. Before it lands, it's not heads or tails. It's in a state of both possibilities at once. This is superposition. A famous thought experiment explaining this is Schrödinger's cat. A cat is placed in a box with a radioactive atom that has a 50% chance of decaying and releasing a poison. Until we open the box and observe it, the cat is considered both alive and dead simultaneously. Another mind-boggling principle is quantum entanglement. This is what Albert Einstein famously called spooky action at a distance. When two particles are entangled, their fates are linked, no matter how far apart they are. If you measure the state of one particle, you instantly know the state of the other, even if it's light years away. It's like having two coins that are magically connected. If one lands on heads, you know the other will instantly be tails. Then there's wave-particle duality. In the quantum world, particles like electrons can behave as both a solid particle and a spread-out wave. The classic double-slit experiment demonstrates this beautifully. When you fire electrons one by one at a screen with two slits, you might expect to see two lines on the detector behind it. But instead, you get an interference pattern, as if waves were passing through and interfering with each other. It's as if each electron passes through both slits at the same time. This leads us to the uncertainty principle formulated by Werner Heisenberg. It states that you can't simultaneously know certain pairs of properties of a particle with perfect accuracy. For example, the more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. It's a fundamental limit on what we can know about the quantum world. Finally, there's quantum tunneling. In classical physics, if you don't have enough energy to climb over a hill, you can't get to the other side. But in the quantum world, a particle can tunnel through an energy barrier it shouldn't be able to cross. It's like a ghost walking through a wall. So, how do we build a computer based on these strange rules? Let's look at the main parts. The heart of a quantum computer is the qubit, which stands for quantum bit. Unlike a classical bit that's either a 0 or a 1, a qubit can be a 0, a 1, or both at the same time, thanks to superposition. This ability to exist in multiple states at once allows quantum computers to process a massive amount of information simultaneously. Qubits are incredibly delicate and can be created using various methods, like trapping individual ions with lasers or using tiny superconducting circuits. The brain of the machine is the quantum processor. This is where the qubits are located and manipulated. Major tech giants are in a race to build more powerful quantum processors. For instance, IBM has developed processors like their Osprey chip with 433 qubits and is working on Condor with over 1,000. Google has its Sycamore processor, which achieved what they called quantum supremacy by performing a calculation in minutes that would take a classical supercomputer thousands of years. Microsoft is also exploring a unique approach with what are called topological qubits. But hardware is nothing without software. Specialized programming languages and algorithms are needed to control the qubits and tell them what to do. These algorithms are designed to exploit quantum phenomena like superposition and entanglement to solve problems that are intractable for classical computers. All of this requires an extreme environment. Qubits are extremely sensitive to their surroundings. Any tiny vibration or temperature change can disrupt their quantum state, a process called decoherence. To prevent this, quantum computers are housed in massive, complex refrigerators called dilution refrigerators. These machines cool the quantum processor down to temperatures colder than deep space, just fractions of a degree above absolute zero. Sophisticated control electronics are also needed to send precise microwave pulses to the qubits to perform operations and read out the results. Now, what can we actually do with these powerful machines? The applications are revolutionary. In cybersecurity, quantum computers could break many of the encryption methods we use today to protect our data. But they also offer a solution: quantum encryption, which uses the principles of quantum mechanics to create unhackable communication channels. In medicine, they could revolutionize drug discovery. By simulating molecules with incredible precision, quantum computers can help scientists design new drugs and materials much faster than is possible today. This could lead to new treatments for diseases like Alzheimer's or more efficient batteries for electric cars. Quantum computers could also supercharge artificial intelligence and machine learning. By processing vast datasets in new ways, they could lead to more powerful AI models, optimizing complex systems in finance, logistics, and climate change modeling. However, it's crucial to understand that quantum computers are not going to replace your laptop or smartphone. They are specialized machines designed for specific, highly complex problems. Classical computers will still be essential for all the everyday tasks we rely on, from browsing the internet to sending emails. Think of quantum computers as a powerful new tool in our computational toolkit, working alongside classical computers to solve some of humanity's biggest challenges. The field of quantum computing is still in its early days, much like classical computing was in the 1950s. There are immense engineering challenges to overcome, but the potential is truly world-changing. We're on the brink of a new technological revolution. Thanks for watching. I hope you enjoyed this journey into the quantum realm. If you found this video helpful, give it a thumbs up, and don't forget to subscribe to LearnLab for more explorations into the future of technology. See you in my next video.